Hello and welcome to our capstone presentation. My name is Joshua Parisi.
I'm Mohammed Abdul Majid.
My name is Majd Al-Slaiti.
And I am Abdullah Al-Gailani.
And we are 2023 UC Chemical Engineering Seniors, Group 2325. In this presentation, we will go over our capstone project titled Commercial Production of VDF-TrFE Polymer. First, let's share with you what our product is. So PVDF-TrFE stands for polyvinylidene fluoride-trifluoroethylene, which is a piezoelectric polymer. Now, piezoelectricity means that the polymer can convert mechanical energy into electrical energy by applying pressure to the material, as seen in the animation on screen. Now, this polymer is used experimentally in battery production as a binder, which has uses in the electrical vehicle production. It's also used in sensors and actuators, and is a candidate for applications in tissue engineering due to its aforementioned piezoelectric properties. There are some downsides with this polymer, such as its extremely high material cost. Right now it costs about $13 a gram, and it's also sold by the gram, which makes it unsuitable for example, electric vehicle production. So we designed a process to solve these downsides mentioned previously. Our process aims to produce 300,000 pounds per year of 7030 PVDF-TrFE in both film and powder forms, and with the objective of supplying the demand in battery market materials for electric vehicles and medical research needs, with the end goal of reducing current market price for the product and increasing supply. Now, the way we did this is we developed a commercial process design by upscaling a current laboratory procedure, which also includes process safety and controls. Now, in the next section, we're going to briefly walk you through the chemistry involved in the process of synthesizing this polymer with Mohammed.
So let's go ahead and take a look at a deeper dive of the production chemistry of PVDF-TrFE from vinylidene fluoride and trifluoroethylene. The first step involves the reaction between VDF and TrFE in the presence of calcium hydroxide and ethyl hydroxyethyl ether, which in our case is our commercial Bermacol, as a stabilizer. This process will be our copolymerization and will result in the formation of a copolymer of both VDF and TrFE. The copolymerization reaction can be initiated by various methods, such as chemical initiators, radiation, or heat. In this case, our calcium hydroxide will act as a base to initiate the reaction between VDF and TrFE, while our Bermacol just stabilizes the resulting copolymer. Our calcium hydroxide will not be a typical initiator in the sense that it will not form any free radicals or any other reactive species that initiate the reaction. However, what calcium hydroxide will do is it will initiate the copolymerization reaction between both VDF and TrFE by deprotonating the acidic hydrogen atoms on the carbon atoms of VDF and TrFE monomers. This reaction will generate carbanions, which are highly unstable, and they will attack the electrophilic double bond of the neighboring monomer, leading to chain growth and propagation. The use of calcium hydroxide as a base initiator is a common method for initiating polymerization for reactions that usually involve monomers with acidic hydrogen atoms, such as in our case VDF and TrFE. The next step will be the functionalization of the copolymer using ethyl chloroformate and diethyl carbonate. The ethyl chloroformate will react with the hydroxyl groups present in the Bermacol to form carbamates, which will act as nucleophiles. These nucleophiles will attack the carbonyl groups of the diethyl carbonate, resulting in the formation of ester linkages between the Bermacol and the copolymer. Bermacol, which is a water-soluble polymer, will stabilize the copolymerization by forming a protective layer around the growing polymer chains, which prevents them from aggregating or coalescing into larger particles. It will also act as a dispersant, which keeps the monomers dispersed or emulsified. The functionalization step, which is the last step of this reaction, will improve the solubility and the processability of the polymer, which will make it easier for us to handle during further processing steps, such as our film casting and our powder form or co-milling. So just the functionalization step will essentially, as mentioned earlier, increase the processability. So before functionalization, the copolymer will be insoluble in most common solvents, and as a result will be difficult to process into useful forms such as films or fibers. This is partly due to the high crystallinity and the polarity of the copolymer, which will limit its interactions with solvents and other materials. By functionalizing the polymer with Bermacol and stabilizing it, as mentioned earlier, Bermacol contains hydroxyl groups. The resulting polymer becomes more compatible with solvents and other materials. As a result, this functionalized polymer is more soluble in a wider range of solvents and can be processed into various forms more easily, which will assist us in our final endeavors before commercializing. I'll walk us through the process overview.
Alright, here's our overall plant breakdown of the processes involved to produce this polymer. The raw material include demineralized water, goes into copolymerization in a reactor, and the tower water is supplied to that reactor for temperature control. The crude product enters the diafiltration system along with demineralized water to remove impurities from the product. And then the product leaves the diafiltration process and flow through a dryer with the compressed air to remove moisture. And then the product at that point will have 99.9% purity and become solid cake. After purifying, this cake product will be milled to produce PVDF-TrFE powder, and 10% of that powder will be transferred to an extruder to produce PVDF-TrFE film. The waste involved from all these processes will be discussed as we go into details through the equipment used in each process on the following slides. There are four main sections in the plant. In blue is the demineralized water system, where demineralized water is produced to supply synthesis section in purple and purification section in green. In purple is the synthesis section where the crude product exits as a slurry, in the green purification section where the slurry is washed and dried, and finally in orange the solid processing section where we turn the product into powder and film. And here is a fluid flow demonstration. The raw material enters the jacketed reactor 2 and yields 90% PVDF-TrFE. Then the crude product, which is a slurry, will go to diafiltration where it will be washed 7 times to produce 99.9% pure product. The fluid then will be transported to a dryer where the moisture will be removed to prepare for milling. And now from the dryer to the co-mill, the product will become powder. 10% of that powder will be transferred via conveyor belts to an extruder to produce the films from this product. Let's take a closer look at each section. This section of the plant includes a unit that is pre-built and fully equipped with the necessary equipment to produce demineralized water from city water. The unit can produce up to 10 gallons per minute, which is stored in an intermediate tank to supply the DI water as a solvent for the reactor, and the very large amount required for the diafiltration system. The DI water is pumped using centrifugal pump, and the possible improvements for this section of the plant is to have another tank for the diafiltration system in case of producing much larger quantities than it's currently issued. Let's talk about the synthesis section. There are 3 tanks contain the reagents along with the demineralized water, the solvent. These tanks have heating coils inside of them, which their purpose is to heat the reagents and the solvent to 105 Fahrenheit prior feeding the reactors. One of the tanks will be fed demineralized water from the demineralized water system, the blue arrow. The tank will contain calcium hydroxide. That raw material tank will contain calcium hydroxide and permacol, as these two materials are solids and there is no significant hazards from mixing them with demineralized water prior feeding into the reactors. In addition to that, the reactors cannot be opened to pour these solid materials, as the reactor needs to be pressurized to complete the reaction. Along with these tanks, we have two gas phase reactants, VDF and TrFE. The pressure of these feed gas canisters are controlled using regulators installed and rated for the reaction requirement. The raw materials will enter one of the two jacketed continuously stirred batch reactors. The reaction takes around 3 hours to complete, and the reactors will operate staggered in 1.5 hour phases to reduce downtime in the purification section and have a semi-continuous process. The jacket around these reactors will be filled with tower water to control the reactor temperature, as we previously mentioned, that the reaction is extremely exothermic, and the temperature can reach around 70 Celsius. Also, the reactors are designed to withstand over 1000 psig, as the laboratory procedure mentioned events of high pressure situation during the copolymerization. The crude product will be a slurry and will be pumped to the purification section. The primary safeguards like temperature control and sensors are listed on the left.
I will be discussing the purification section of the plant. So once the crude product comes out of the reactor, it will be sent to a diafiltration system where we'll be purifying our product to remove all the impurities. The system consists of a washer tank equipped with a mixer. The fluid is pumped using a positive displacement pump, as the fluid in the stage will become viscous at this stage of the process due to the nature of the polymer in water, along with the dispersion of Bermacol. The solvent used is DI water, supplied from the DI water system that we talked about earlier. And so an amount equal to the crude product is fed to the system. However, the total amount will be added is equal to 7 times the amount of crude product. This will dissolve the impurities, including the calcium hydroxide and other materials participated in the reaction. The mixture will then be transported to an ultrafiltration membrane to separate the dissolved impurities, along with a considerable amount of DI water, as the permeates fluid and the pure product will remain in the retentate, which will flow back to the washer tank with a fresh batch of DI water. This process will have 7 washing cycles to obtain a 99.9% pure PVDF-TrFE polymer. In every wash, the permeate will be sent to a qualified treatment plant to properly remove these hazardous chemicals, and the system is maintained at a steady state by feeding the washer tank an equal volume of the permeate exiting the diafiltration. The diafiltration process will take around 30 minutes. Once the product is purified, a 70% moisture content will replace the impurities, which will be evaporated using the fluidized bed dryer. This fluidized bed dryer uses compressed air pumped from below the trays through the fluid, leaving from the top. The operating temperature of the dryer will be around 100 degrees Celsius to evaporate the water, and once dried, the solid product will be transferred via conveyor belts to the solid product processing section, which I'll be talking about in the next slide. Moving on to the solid processing section. So exiting the dryer, as we said earlier, is a 99.9% pure solid PVDF-TrFE copolymer agglomerate. And this agglomerate, the dried copolymer, it'll be sent to the conical mill via conveyor belt. The conical mill will mill the solid copolymer to achieve the deagglomeration and the particle size reduction in order to later extrude this powder into a film. The co-mill will have a wide selection of screen sizes and rotor configurations, which will enable us to achieve the desired particle size distribution. The time to mill the 51-pound batch of dried copolymer will be approximately 15 minutes. 90% of this milled powder product will be sent via powder bins on a conveyor belt to be stored as a final product, where 10% of the milled powder will be conveyed to a film extruder. When the milled powder is fed into the extruder, as you can see is the last unit operation in the plant, it is melted through a heated barrel and then subjected to a high pressure and shear forces, which will homogenize the material. The molten polymer is then directed through a narrow die, which will shape the polymer into a thin film. And the film is finally quenched and solidified and then cut into sheets as the final product. This extrusion process will take approximately 15 minutes to complete. And now we'll be talking about process safety, which will be introduced by Muhammad.
So the table below showcases a summary of the compounds used alongside their respective health, fire, and reactivity hazards. The team conducted a process hazard analysis, or PHA analysis, utilizing the what-if methodology to guide the implementation of any controls and safeguards. The controls and safeguards were showcased during each respective section as seen beforehand. The biggest open point as a result of this what-if analysis was the quantification of the amount of byproducts, both gaseous and liquid, formed as a result of the reaction. We will go more in depth on that avenue in the environmental performance section. As far as other recommendations go, the team recommends the application of secondary temperature control system in both the reactor and the dryer. And what we believe this will do is it will serve as an additional layer of protection against subtle spikes in temperature that may introduce a risk of fire or explosion. This will also be compounded with the safety factor that would come alongside a better understanding of the kinetics of the actual reaction. The team will also recommend the implementation of external protective barriers around pipes and areas of potential physical external damage. Finally, a robust preventative maintenance plan will be implemented for each node in the plant. The maintenance plan is to be performed consistently as well as timely. Closer look at the environmental performance of our process. The biggest open points as far as environmental performance is concerned is the release of trace amounts of diethyl carbonate as well as ethyl chlorformate. The team found out that ethyl chlorformate decomposes in the presence of sunlight to produce acid fumes, while diethyl carbonate still remains an open point. The team has been considering the use of flares, or small-scale flares, in order to break down diethyl carbonate. This will also break down ethyl chlorformate as they both break down the presence of heat. The table on the top also showcases the effect on water life if exposed to any of the chemicals. That, as well as the waste stream analysis, was pulled out from an estimate derived from ChemCAD and remains as is, a very rough estimate. A further analysis is recommended in order to determine a better approximation of the impact. But as it currently remains, there is a low contribution of the waste stream towards environmental impact for both water as well as global warming, smog formation, and acid rain. Here is a summary of all the other regulations considered so far. The biggest regulation that led to a safety recommendation can be showcased in section 1503.2 of the Greater Cincinnati MSD regulation. This led to the installation of lower explosive limits, or LEL sensors, for the detection of volatile compounds. This proved as a crucial safeguard for operators and the process, and the impact of which was evaluated and can be showcased on our PHA report.
So regarding the significant technology risks, the primary risk associated with this project is the adaptation and scale-up of a lab polymerization procedure. We don't have a perfect understanding of the kinetics of the reaction, but the synthesis of the PVDF-TrFE is currently only done at a laboratory scale, as far as we know. Thus, scaling it up and producing hundreds of thousands of pounds per year of the material has never been done before, and there's definitely some risk that would not react as anticipated. So scaling up the reaction may also change the kinetics, which may affect the reaction conditions and the expected yield. So to mitigate this risk, pilot trials for this synthesis should be completed before scale construction begins. Another technology risk entails the availability of TrFE, trifluoroethylene. The process requires about 120,000 pounds per year of the material, and it's not a very common chemical reagent. The risks of not having enough raw material or paying a premium on TrFE once full operation is achieved. The risk can be mitigated by synthesizing TrFE on site, via dehalogenation of fluoride-trifluoroethylene, which is less expensive and more available. And finally, adapting the lab procedure also entails a new control system. The control system includes reagent injection, timed reagent and initiator additions, and product removal. Running the reaction at such a high pressure also means a consideration needs to be made for the relief system and what tolerances are allowed by the reaction kinetics.
So now we come to the process economics. So our design is intended for us to sell the two forms of the PVDF-TrFE. So the powder is sold at 8 cents a gram, which is significantly better than the $13 a gram as mentioned in our intro. And the film is marketed to be sold at 50 cents per gram. Now the estimated revenue from this in total is $16.6 million a year. Using the individual factors method, as explained in the textbook, our capital costs are estimated at about $8.9 million. And the breakdown of that can be seen in the table, with our total bare module cost at $2.7 million, our total permanent investment at $6.9 million, and our working capital at $2 million. Now our expenses is topped by our raw material expenses at $3.7 million. We designed this process to use as few utilities as possible. So our utilities actually come out to around $40,000 a year. Operational cost is another $2 million, and then all other expenses totaled is about $3.8 million. So the profits earned from this design post-tax, it comes out to about $4.3 million per year, which this equals a return on investment of about 48%. So based on expected sales, expenses, capital costs, this project is expected to be profitable and is recommended for that reason. Now, other metrics of profitability we can showcase this as is venture profit, which is about $2.3 million. This whole project is expected to have a payback period of about 1.3 years, which means the whole project will be, the initial capital investment will be paid back in only less than 1.5 years. The net present value over the course of its 10-year life, with a 15% discount, is about $10.5 million. And the investor's rate of return comes out to about 36.6%.
Although we had a thought out and completed idea for a plant to produce the PVDF-TrFE, there is still some future work and recommendations to be done. So first of all, the temperature and pressure conditions at which the reaction is carried out can be optimized to identify conditions that result in higher yield and improved polymer properties, as well as decreasing the likelihood of potential hazards associated with the reaction conditions. Other than that, alternative reagents, including different catalysts, initiators, stabilizing agents, and so on, can be used to improve the overall reaction kinetics and conditions of the reaction. Also, to optimize the diafiltration system that purifies the product after copolymerization, future work can focus on investigating the impact of a membrane composition and pore size, buffer solutions, and pH levels, as well as the process conditions such as the agitation speed and feed rate. This could lead to improved separation and removal of impurities, enhanced selectivity, and a higher purity of the final product. Besides this, the fluid bed dryer can be optimized for its performance, including investigating the effect of particle size and morphology on the drying process, as well as studying the impact of inlet air humidity and drying rate and efficiency. And this can lead to identifying the optimal particle size range and morphology for the fluidized bed dryer. Finally, the co-mill, which mills the product, the parameters of that can be refined to improve the milling duration and the final particle size distribution and quality. And the extrusion process can focus on optimizing the parameters, such as evaluating the effect of incorporating additives or fillers, and understanding the impact of different cooling methods on film properties. Different things like this for the extrusion process can improve the properties of the polymer, such as the mechanical strength, thermal stability, and electrical conductivity and piezoelectricity. Thank you very much for listening to our project, and I hope you have a great day.